So now let's talk about left ventricular hypertrophy. So in left ventricular hypertrophy is when the muscle of the left ventricle is very big. So there will be a lot of electrical activity in that part of the ventricles, and increased muscle activity, increased electrical activity means you get a longer QRS complex, because QRS complex represents ventricular depolarization. So in left ventricular hypertrophy, because there's so much more muscle on the left side now, you get left axis deviation. So you can see this, lead 1 and 2 are pointing in opposite direction. So 2 is pointing downwards, 1 is pointing upwards. So you say they've left each other, so left axis deviation. And also the R waves, which is the positive deflection in the right ventricular leads are usually long. There are lots of rules. One of them is that V5 or V6 is longer than 25 millimeters. So if you look at this, so this is probably borderline. Let's go for V6. If you count the number of small squares, is a lot actually. 1 2 3 4 5 6 7 6 times 7 times 5 is 35 plus 3, so there are 38 small squares in this. So that's very long. That meets the criteria. There's another criteria that the R wave in V5 or V6 plus the S wave in V1 or V2 is longer than 35 millimeters. So when you count the number of small squares of the R wave on the left side plus the S wave on the right lead, it's a lot. The reason why the S wave is longer in the right lead, remember the right lead is picking up the wave of depolarization of the left ventricle. So if there's left ventricular hypertrophy, that wave of depolarization will be increased. So there will be a bigger negative deflection when you are looking at it from the right lead. So this is the S wave. So 1 2 3 4, that's about 20 small squares of S wave plus the 38 we counted as 58 small squares, 58 millimeters. So there's left ventricular hypertrophy. Okay. There is also, remember in my first video I said whenever there's electrical abnormality in the QRS complex, there's usually electrical abnormality in the T wave as well, because T wave is repolarization. If the depolarization is abnormal, the repolarization could end up being abnormal as well. So you can get inverted T waves in the lateral leads. So because the left ventricular leads are the ones that have the abnormal QRS, so you have abnormal T waves in the lateral leads as well. And you could also sometimes get in V4, because V4 is kind of halfway between the right ventricular leads and the left ventricular leads. Okay, so you can see the inverted T waves. So look at that, that's an inverted T wave there, inverted T wave. There's T wave inversion there as well. That's a lateral lead. There's T wave inversion there too. So the lateral leads have inverted T wave. In this case, there's no T wave inversion in lead 4. The T wave is upright. Okay, right ventricular hypertrophy. So you get bigger muscle on the right side. The right side takes over in terms of wave of depolarization. The wave of depolarization will be more towards the right. So you get right axis deviation. So in right axis deviation, the two lead 1 and lead 2 are no more pointing upwards. So let's look at the graph at the ECG strip. In this case, lead 1 is pointing downwards, mostly downwards. Lead 2 is pointing mostly upwards. So even though they are in opposite direction, they are still meeting each other. So they are going towards each other. So you say the love is still alright. So there's right axis deviation. Also, because the wave of depolarization is more towards the right now, Sorry, because the wave of depolarization is now mostly to the right, so the average direction is to the right, you get long R waves in V1. So V1 you would have the R wave will be longer than the S wave. Remember, normal V1 has short R wave and very long S wave, but in right ventricular hypertrophy you get long R wave and shorter S wave in S1, in V1 or V2. Okay, if you look at this, you can see that in this the R wave is quite long. There's very short S wave there, and this as well. Yeah, so you can see that the short S wave. So the R wave is very long in this. Or there's another rule that says the R wave in V1 plus the S wave in V5 or V6 is more than 10. Yeah, you can count this. So that's another rule. Or you could also get T wave inversion in the right ventricular leads. Remember, if the right ventricular leads, if the depolarization is abnormal, you could get abnormal repolarization. So you could, in this one, you can see there's inverted T wave there. So inverted T wave in V1, V2. There's also inverted T wave in V3 as well, and also in V4. So that's what happens in right ventricular lead. So let's do a case. So pause the video and try to answer this question. So the first thing you do, you have to look at the rhythm. Is it regular or irregular? So get your piece of paper, draw your 3 lines, and then slide your paper. Do the points match? In this case, a match. So you say it's a regular rhythm. Okay. Is this sinus rhythm or atrial or ventricular or junctional? So first of all, let's think, is this a supraventricular rhythm or ventricular rhythm? So the QRS complex is less than 120 small squares. So we say the QRS duration is normal, so it has to be a supraventricular rhythm. And if you look at the P waves, you have P waves, normal P waves present. So this has to be a sinus rhythm. So sinus rhythm, P waves present, QRS less than 120 milliseconds, and then regular interval for the QRS complexes. Okay, now calculate the rate. So the rate will be 1500 divided by number of small squares. If you count number of small squares there, that's 25. 1500 divided by 25, you get 60 beats per minute. Now let's look at the cardiac axis. One is pointing upwards, two is pointing downwards. They are leaving each other, so they are pointing in opposite directions. So if they are going in opposite directions, that means they've left each other, so it's left axis deviation. Okay. And pause the video once again and try to answer this question. Okay. So where can you find Q waves in this ECG strip? Start from lead 1. Is there a Q wave there? No. Lead 2? No. Lead 3, I can see that the first deflection is negative, so there's Q wave in lead 3. Okay. Now let's go into remember AVR is forgotten lead. AVL, no Q wave. AVF, you can see there's a Q wave there, and the Q wave is more than 1 small square wide, and is also more than 2 small squares deep, so it's abnormal. So you can say we have inferior, because 3 and AVF are inferior leads, so you can say there's an old inferior MI. Okay, now let's look into the precordial leads. There's a Q wave there, So V1 has Q wave, V2 you can also see Q wave there, V3 you can see Q wave. So those are, yeah, so V1, V2 and V3 Q waves. So this V1, V2, V3, look at the anterior part of the heart. So you say there's also old anterior MI. So now which coronary arteries supply the inferior part of the heart? So is the right coronary artery, and the anterior part, left anterior descending artery. Okay. And pause the video. Okay. So if you look at this ECG, obviously you do the sequence, but I've already given you the option. You can see that there's actually very long QRS complexes on the right leads. So you should start suspecting, could there be possible right ventricular hypertrophy? Look at the long R waves. The R waves are quite massive on this. So there's possible right ventricular hypertrophy. Now look at your cardiac axis. Okay. So lead 2 is up, lead 1 is down. They are no more, both of them are no more positive, so there's definitely axis deviation, but they are still meeting each other, so they are pointing to each other. So the love is all right, and so there's right axis deviation. So right axis deviation, very long R waves in the right ventricular leads, and you can also see that there's inverted T waves in the right ventricular leads as well. So that should be pointing you towards right ventricular hypertrophy. And also talking about conduction, you can see if you this QRS wave, QRS complex is more than 3 small squares, so it has to be abnormal conduction. The conduction is not normal in this because it has to be less than 3 small squares. Also, if you look at your PR interval, remember PR interval should be 3 to 5 small squares. This is about 2 small squares, so there's shortened PR interval. And if you look at the QRS complex once again, you can see that there's a delta wave. So this is known as Wolff-Parkinson-White syndrome. It's an abnormal conduction of electrical impulse from the atrium to the ventricles. We'll talk about that in a future video. So the answer to this question is A. Normally you should go through the sequence, but I'm just picking out the abnormalities in this for this video. Okay, so we've try to answer this quiz again, and pause the video, answer the quiz questions. The answers are on the next slide, so pause the video. Now, so today we've talked about leads, cardiac axis, and the P wave morphology. So leads, just remember, draw your Y shape and then add 1, 2, and 3. And the ones pointing downwards are the inferior leads. The ones pointing to the left are the lateral leads. Okay, and those are the limb leads. And then you have the chest leads. So just remember the points of attachment. 1, 2, 3, and 4 are in front, so the anterior leads. 5 and 6 are the side of the patient, so they are lateral leads. And then look at the heart in the horizontal plane. So that gives us these leads: septal, anterior, inferior, and lateral leads. And we also talked about the coronary artery anatomy. So the left anterior descending supplies the anterior part, the circumflex supplies the lateral, and then the right coronary supplies the inferior. cardiac axis. We talked about the love story. Both of them are pointing upwards in the same direction, lead 1 and 2. Both of them are positive, that's normal relationship. And if both of them are pointing in the opposite direction, so one is pointing down and 2 is pointing up, both of them there's now deviation in their love, but it's still alright because both of them are still meeting. But if one is pointing up and 2 is pointing down, then they've left each other, so there's left axis deviation. And also in P wave morphology, we talked about P mitralis, so that's broad and bifid P waves. So mitral valve is on the left side, so remember left atrial hypertrophy, and P pulmonale is peaked P wave, which represent right atrial hypertrophy. The pulmonary circulation is on the right side, so P pulmonale, right atrial hypertrophy. Okay, QRS complex. We talked about the shape of the QRS waves in the right ventricular leads and left ventricular leads. We mentioned that the septum is the first to be depolarized, so there's okay, and the septum is depolarized from left to right, and that in a normal heart, the left ventricle is the one that influences the ECG the most. Okay. So this is a V1 ECG QRS complex, because the first depolarization, so V1 will be there. Q wave, not Q wave, sorry, it will be picking up this because that's going towards V1, so you get small deflection. But after the septum is depolarized, and you get ventricular depolarization on the left, and because it's going away from the V1 electrode, it will give you a downward deflection, and then you go back to the baseline. V6, which is a lateral electrode or left ventricular electrode. So the first thing to look at, the septum is moving away, so there will be a very tiny Q wave because the wave of depolarization is moving away. And after the septum is depolarized and you get the left ventricular depolarization there, it will pick that up, and then there will be a very tall R wave, there will be a massive R wave, and then it will fall back to the baseline. So this is just to compare the difference between V1 and V6 electrodes. So because the left lateral leads and the lateral leads pick up Q waves just like V6, you should typically see small Q waves in the lateral leads. However, pathological Q waves, these are the conditions. So if it's more than one small square wide, or more than one small square, two small squares deep, or if there's if you see it in the V1 to V3 electrodes, you shouldn't be seeing Q waves in them. And we talked about electrical hypertrophy. The height of the QRS complex represents the voltage, and which is based on the electrical the amount of muscle you have in that part of the heart. So let's say right ventricular hypertrophy, there will be more muscle in the right part of the ventricles, the right ventricles. So that will lead to right axis deviation, because that will be making the wave of depolarization go more towards the right. And you would also have long R waves in V1. The R waves will be longer than S wave, which is in contrast to what we have here. Okay, and then you have inverted T waves, because usually when the wave of depolarization is abnormal, then the repolarization will be abnormal as well. Okay, now left ventricular hypertrophy. So you get long R waves. You get left axis deviation, because there's so much muscle on the left side. Now the wave of depolarization is even pushed further to the left, so you get left axis deviation, and then you get long R waves, because if there's so much muscle there, then this wave will be massive, so this R wave will be longer. So you get, and these are the conditions. So if the V5 or V6 R wave is longer than 25 millimeter, or if the R wave in V5 or V6 plus S wave in V1 or V2 is more than 35 millimeter, then there's possible left ventricular hypertrophy. Also, we talked about the inverted Z waves. If depolarization is abnormal, repolarization tends to be abnormal as well. And from my last video, so if there is normal duration, the normal duration of QRS complex is less than 120 milliseconds. You can watch my old video to see the factors that could affect QRS duration. Why could QRS complex be wide? Thanks for watching the video. This is my reference where I got my information from. If you have any question, please post it in the comment section. And also, I'm open to feedback. Let me know what you need me, what I've done well, and what you would like me to improve. Thank you.